In this video we'll be looking at changes in momentum and their implications on various situations. This section is only for physics GCSE. It doesn't apply if you're doing the trilogy. Towards the end of this video we'll be having a look at various questions that have come up at GCSE and how you would go about answering them. So what does the syllabus say? It says that when a force acts on an object that is moving or able to move, a change in momentum occurs. You're told that the equations F equals ma, that's the second law, and A is change of speed over time, you should know that one, combine together to give you another equation, which is the force would be the change of momentum, which is written m delta v, divided by the change of time, which is written delta t. And therefore the force equals the rate of change of momentum. So let's see how this works then. We have here two equations that you should already have memorized. So from Newton's second law we have force is mass times acceleration. And we also know from the forces topic that acceleration is the change of velocity divided by the time taken for that change. So what we do is a thing you've done in maths, you do a process of substitution of something from one equation into another equation. And you may well have done this when you've been solving simultaneous equations in maths, for example. So if force is mass times acceleration and acceleration is change of velocity divided by the time, then in the first equation you can insert change of velocity divided by the time taken. And that will give you force equals mass times the change of velocity divided by the time taken for that change. Now, having got to that equation, we now know that mass times velocity is momentum. So we can rewrite that equation as the force is the change of momentum divided by the time taken for that change. And so in English that would be the force is the rate of change of momentum. How quickly the momentum changes equals the force. So if the force is related to the rate of change of momentum, it leads us to two important conclusions or implications which we are going to use time and time again through your questions in the latter part of this video. So implication number one, if the momentum changes quickly, there is a large force. If the momentum changes slowly, there's a smaller force. So let's look at one implication of that. We have here somebody kicking a stone and somebody kicking a football. Now we know that the stone is a hard surface, it's not got any give in it. The football, however, is softer and it's got some give in it. As you kick it, the surface compresses in slightly. And so when you're kicking the stone, you might have a contact time of about 1/100th of a second. Whereas in the football, you've got a longer contact time of maybe 1/10th of a second. And because of that, that's going to give us a difference in the force that you feel when you kick those two objects. Now let's assume that those two have got the same mass. In the top one, if you're kicking the stone, if the momentum changes quickly, 1/100th of a second, there's a large force. And so that hurts. In the second one, if the momentum changes slowly, there's a smaller force. Now we've got 1/10th of a second here, 10 times more contact time. And therefore you're going to end up with a smaller force, which is why it doesn't hurt when you kick a football. So back to the specification again. Students should be able to explain safety features such as airbags, seat belts, gymnasium crash mats, cycle helmets and cushioned surfaces for playgrounds with reference to the concept of a rate of change of momentum. And then students should be able to apply equations relating force, mass, velocity and acceleration to explain how the changes involved are interrelated. And so on to the questions. I've got a selection of questions here from previous GCSE examinations, and in each one you'll have a question slide followed by an answer slide. And the recommendation would be to pause the video, have a go at the question, and then compare your answer with the one on the second slide. So here we have a diagram where we have the arrows representing the horizontal forces acting on a motorbike at one moment in time. You're told the mass of the motorbike and the rider is 275 kilograms, and you're asked to calculate the acceleration on the motorbike at this moment in time. So here we're given some forces, we have a mass, so you should know that the equation you're going to use is the force equals mass times the acceleration. But according to Newton's second law, it's the resultant force we're interested in. So that's the first thing to work out. 2000 newtons forwards, 845 newtons backwards, giving you a resultant force of 1155 newtons to the right. The acceleration will be that force divided by the mass. When you do that, that gives you 4.2 meters per second squared towards the right. So this question continues as follows. Of particular concern to motorbike riders is the design of steel crash barriers. Riders falling off and sliding at high speed into a steel support post are often seriously injured. One way to reduce the risk of serious injury is to cover the post in a thick layer of high impact polyurethane foam. You're asked to use your ideas of momentum to explain how the layer of foam reduces the risk of serious injury to a motorbike rider sliding at high speed into the support post. So what I've tried to do here in my 3 sentences is I've started off by talking about the momentum change. Secondly, what would happen if that happened quickly? In other words, with the steel post without the foam. And then what would happen if it happened slowly with the steel post with the polyurethane foam? So I've written, if a rider slides into a post, the momentum changes to 0. If this happens quickly, they will experience a large force resulting in serious injury. If the post is covered with the foam, the momentum changes more slowly, so the force is smaller, resulting in minor injuries. Now this second question is very similar to the second part of that first question. You should be able to pause the video and have a go at this one. So this time we have a diagram showing a padded body protector which may be worn by a horse rider. If the rider falls off the horse, the body protector reduces the chance of the rider being injured. Use the idea of momentum to explain why. So hopefully what you wrote will be something like this. If the rider falls off the horse, the velocity will increase towards the ground. Momentum is mass times velocity, so their momentum increases. When they hit the ground, their momentum decreases to 0. And then, as you've done before in the previous one, if the momentum changes quickly, the force they experience will be greater. If they are wearing a padded body protector, it takes more time for their momentum to change, so the force is smaller, so the risk of injury will be smaller. Now, do use the same phrases in your answer that are used in the question. So the question talks about a padded body protector, so use that phrase within your answer. The question specifically asks about reducing the chance of the rider being injured, and so you need to use that type of phrase within your answer. So I've talked about the risk of injury being smaller. Here we have a diagram showing a car before and during a crash test. The car hits the wall at 14 meters per second and takes 0.25 seconds to stop. We want the equation linking acceleration, change of velocity and time, and then calculate the deceleration of the car. Now I would stress in this first question that you actually use the words they've used in the question. So the question talks about acceleration, change in velocity, time taken, and so those are precisely the words you need to use in your answer. So it's acceleration equals change in velocity divided by time taken. Now lots of people will try and shorten that to acceleration is velocity divided by time or something like that. Not best practice. Use the terms that are used in the question. The numbers you've got in the question, so the change in velocity is 14 because it's gone from 14 meters per second to stop. So the change is 14. The time is 0.25 seconds. When you do that division, you'll end up with 56 meters per second squared. So we have a slightly different style of question here because they're starting the answer off for you. For some people, that will make it easier. For others, it actually makes it harder. So in an accident, the crumple zone at the front of a car collapses progressively. This increases the time it takes for the car to stop. In a front-end collision, the injury to the car passengers should be reduced. Explain why. The answer's been started for you. So you start by increasing the time it takes for the car to stop there. So this is one possibility here. By increasing the time it takes for the car to stop, the momentum changes more slowly, so the force is lower. This means the forces on the passengers will be lower, reducing their chances of injury. Now this question contains some difficult aspects, and some students find this style of question very, very difficult. So you're told during flight, air enters an engine, so this must be an aeroplane engine, at 175 meters per second, and it leaves at 475 meters per second. A forward thrust of 105 kilonewtons is produced. Use the equation to calculate the mass of air passing through the engine every second, and they tell you to ignore the mass of the burnt fuel. The equation to use is the force is the change of momentum divided by the time. Of course, you've got to know that momentum is mass times velocity, and that is one of the keys to get into this question. So have a go and then continue the video once you've got an answer. Now, one of the keys for this sort of question is to have a look at your time and think to yourself, okay, it's 175 meters per second, which means each second, which means that the time I'm considering for this question is 1 second. Now this is why I've listed down what you know. So you have the time is 1 second. Your starting velocity is 175 and your final velocity is 475, giving you a change of velocity of 300 meters per second. The force, you have to be careful, it must be in newtons. So kilo means 1,000, so this is 105,000 newtons. Now once you've got that, I've changed the equation from change in momentum divided by time to mass times velocity divided by time. Now the time is 1, which means that mathematically the force is the mass times the change of velocity. I can rearrange that to give me mass is force divided by velocity, which gives me 105,000 divided by 300, which gives me 350 kilograms of air. Remember, that is each second that's passing into the engine. Now this is much more straightforward. Diagram showing a hammer just about to drive a nail into a block of wood. The mass of the hammer is 0.75 kilograms. Its velocity just before it hits the nail is 15 meters per second downwards. After hitting the nail, the hammer remains in contact with it for 0.1 seconds. And after this time, both the hammer and the nail have stopped moving. They want the equation for momentum. They want you to work out the momentum of the hammer, and then they want the change in momentum of the hammer during the time it's in contact with the nail. So pause video, have a go at that, compare your answers when you restart. So we can write down momentum is mass times velocity. We use the figures in the question, so we have a mass of 0.75 kilograms. We've got a velocity of 15 meters per second. We multiply those and we get 11.25. It wants the unit, so that's the unit for mass multiplied by the unit for velocity, so it's kilogram meters per second, and the direction is going to be downwards. Now, a lot of people get stuck on the next sort of question that follows. Do look at the number of marks. It's just one. Now, if it's 1 mark, it's doubtful it's going to be asking you for anything in terms of more calculations. You should be realizing that the momentum, that's the momentum of the hammer you've just worked out, 11.25, and now you're being asked for the change in momentum of the hammer. Well, in the question it tells you the hammer has stopped moving, which means its momentum is now 0. So it's changed from 11.25 to 0, so what's the change? 11.25. That's why they're only offering you 1 mark for that. Then following on from this, write down an equation connecting change of momentum, force and time, and then calculate the force applied by the hammer to the nail. So for the first part, remember to use the phrases that are used in the question. So you'll write down the force is the change in momentum divided by the time. From the previous bit of the question, we got the momentum change was 11.25, the time's 0.1 seconds. We divide those two, we'll end up with 112.5, and therefore the force is 112.5 newtons. This is the second part of the hammer question. Just keep on practicing these. Once you get used to the way of doing it, it'll just flow off your pen when you're in your exam. Very frequently asked, these questions. So a magazine article states that wearing a seatbelt can save your life in a car crash. Use your understanding of momentum to explain how this is correct. So take a few minutes, maybe 3-4 minutes, write out your answer for that, and then compare it with mine. So I've written that in a car crash, the velocity of the car changes to 0. The momentum also changes to 0 because momentum is mass times velocity. If the initial momentum is large, in other words, the car's going fast, and it changes quickly, the forces involved are large. The use of a seatbelt means there is more time for your momentum to change, so the forces on you are smaller, reducing the possibility of life-threatening injury. If you hit the steering wheel or the windscreen, the time for your momentum to change will be much smaller, increasing the forces on you. Now you'll notice that I've used my understanding of momentum. I've said what it is, mass times velocity. I've linked it in with saying what happens to velocity in the car, and I have talked about saving your life, relating that to life-threatening injuries. Okay, on to our last question. We have here a small radio-controlled flying toy. A fan inside the toy pushes air downwards, creating the lift force on the toy. So we've got a weight there of 0.6 newtons. When the toy is hovering in mid-air, the fan is pushing 1.5 kilograms of air downwards every 10 seconds. Before the toy is switched on, the air is stationary. So use the equation to calculate the velocity of the air when the toy is hovering, showing how you'd work out your answer. Now I've used one particular method to solve this by just considering what's happening in 1 second. There is another way which would end you up with the same answer. So our initial speed of the air is 0. The mass of air is 1.5 kilograms every 10 seconds, which means every 1 second it's going to be 0.15 kilograms. So now I've got both my things in per second, meters per second, kilograms per second. So my time is 1. The force when hovering is 0.6 newtons upwards, and that is equal and opposite to the weight force, giving me a resultant force of 0. We're told that the toy is hovering. That means it's not moving up or down. So if our time is 1, then force is mass times velocity, which means that my velocity is the force divided by the mass, 0.6 divided by 0.145, which gives me 4 meters per second. Okay, have a go at this one. Explain why the toy accelerates upwards when the fan rotates faster. So I've written, if the fan rotates faster, a larger mass of air flows through it. This produces a larger force upwards. The upward force is now greater than the downward force, so there is a resultant force upwards, so the toy accelerates upwards. And that's according to Newton's second law. And so here it is again. The third part of this question tells you the toy is not easy to control, so it often falls to the ground. Explain how the flexible polystyrene base helps to protect the toy from being damaged when it crashes into the ground. So have one more go at that sort of question. You know what you're doing, I hope, by now. So here's my answer. When the toy crashes to the ground, its velocity changes to 0. Momentum is mass times velocity, which means its momentum also changes to 0. If this change happens quickly, the force on the toy is great and it may break. The flexible base allows more time for the momentum to change, meaning a smaller force on the toy, so it's protected from being damaged. Now, my last little phrase there, protected from being damaged, that is abstracted straight from the question. I do encourage you to do that. Use the phrases in the question to make sure you're answering the question. To explain how the flexible base, I've used that phrase, helps to protect the toy from being damaged, I've used that, and crashes into the ground, I have used that phrase in my answer as well. So that's just a useful exam tip to use the phrases in the question in your own answer. It shows the examiner you have actually read the question and that you are actually answering it.